Alrighty. Okay. So my streak is now renewed to 0 because I couldn't solve a medium problem. To be fair, that was a very hard medium problem yesterday, and I really didn't have much clue as to how to approach it. Still thinking about it. Anyways, find triangular sum of an array. You're given a zero index integer array nums, where nums i's digit between 0 and 9. Okay. Find triangular sum of nums. Find the triangular sum of nums. Oh, the triangular sum of nums is the value of the only element present in nums after the following process terminates. Okay, so maybe the values disappear. Let nums comprise of n l elements if n equals 1 and the process otherwise create a new zero index integer array, new nums, length n minus 1 for each index I between 0 and n minus 1. Assign the value of new nums as nums of I plus nums of I plus 1 mod 10. Oh, so you're combining adjacent, or you're combining consecutive digits in the array at each iteration mod 10. Okay, this one I think, well, at least I understand it pretty quickly. 1 plus 2 combines to 3, 2 plus 2 combines to 5, 3, 4, 7, 4, 5, 9, 3, 5, 8, 5, 7, 12, mod 10 is going to be 2, 7, 9, 16, mod 10 is 6. Okay. So in modular arithmetic, I'm pretty sure that the number of times 2 contributes to the total is, I think, like this 3 has a 2 in it. So so if I think about the second layer, 3 plus 5 plus 7 plus 9, that's the same thing as 1 plus 2. Well, yeah, this is obvious, but 2 plus 3 plus 3 plus 4 plus 4 plus 5. So in the second layer, you have like 1, you have 2 2s, you have 2 3s, you have 2 4s, and you have 1 5. So in the third layer, 3 and 5 combine. So this combines with this. So this, I think in the end, 1 appears once in the overall sum. So if I didn't like, oh, but then it does have modulo 10, so it doesn't actually, so these things don't actually, 1,000 long. So it shouldn't be, probably shouldn't try to simulate it. Well, 1,000 times 1,000 is 1,000,000. Maybe you can simulate it, to be honest. Boolean operations is kind of slow though. Can't sort it, I don't think. So the 2 here appears here. That appears here. Try to consider whether or not let's go ahead and do a test case here. I feel like the 1 and the 5 being at the ends makes a difference, but does the order matter? Like if this is 4, 3, I'm guessing it might not. Interesting. The order does matter. I was thinking maybe the middle, they changed the UI. I was thinking maybe for some reason the order of the terms outside the first and last might not matter. But it definitely does. Okay. Let's do the slow approach first, or the possibly slow approach, which is kind of the just following the rules. So let's say while length of nums is greater than 1, I'll modify nums each time. Let's say new nums is an array for every I in or k in range of length of nums minus 1, since I need to access nums at k and nums at k plus 1. New nums dot append the value of nums at k plus nums at k plus 1 mod 10. And then afterwards nums becomes new nums. And then return the last value. Again, I think this might be too slow. Okay. Yeah, wow, that's really fast. 13 milliseconds. Okay, but this is definitely just the, there might be maybe there's a list comprehension way of forming the, let's say there's a list comprehension way of forming this. Let's go list comprehension way. List comprehension way I think would be something like new nums equals the value that is nums at k plus nums at k plus 1 mod 10 for k in range length of nums minus 1. Okay, I think this is the list comprehension way of doing that. and then I'll say nums equals new nums. This should be the same speed, maybe slightly faster, since it doesn't use a for loop. And this is a kind of normal loop. Still not fast enough. Okay, so trying to think of there's some underlying math structure of the value here. Kind of. Let's have the mod 10 bit. Okay, so let's think about this. If I didn't do mod 10, what happens if I don't do mod 10? No. So if I have 12 plus 12, that's 24. The mod 10 is kind of necessary, otherwise the numbers get too large, possibly. Otherwise the numbers get too large. But 12 plus 12 is 24, which mod 10 is 4. Just like, and 12 is 2 and 2. So I think maybe if you didn't do the mod 10 bit, or if you don't worry about the mod 10 bit, and mod 10 the final result is still the same. So in that case, then it's just a matter of thinking about how everything contributes, the number of contributions each of the initial values makes to the overall result. So in that case, it'd be something like in that case, it would be something like 1 plus 2, 2 plus 3, 3 plus 4. So isn't it binomial? The number times 2 contributes to this thing. 1 contributes once, because 1 is only in here. 2 contributes these 2. Okay, I think it might be binomial. So the 5th level binomial expansion should be like 1, 4, 6, 1. Oh, 1, 4, 6, 4, 1. So I have 1 plus 2 times, well, 4 times 2 plus 6 times 3 plus 4 times 4 plus 5, no, 1 times 5. So that's 1 plus 8 plus 18 plus 16 plus 5. No, that's not. Oh, whoops. No, that's right. Okay. 8 plus 18 is 26. 26 plus 16 is 42. 42 plus 6 is 48. Okay. Yeah. So the end sum is the binomial expansion. The n sum could be determined by using the binomial coefficients for that expansion, for that row on the initial values in the nums. So you do each value times its binomial coefficient and take those sums, take the sum of those products and do mod 10. Binomial coefficients. Binomial coefficients. How do you find the binomial coefficient of the nth row? You could so it's going to be NCR binomial coefficients. So if it's, let's say, row 5, or I guess this is row 4, the first row is row 0, row 4, I think. So 4 choose 1, 4 choose 0, 4 choose 1. 4 choose 2. What if there's a way to use a for loop to get those coefficients, and then if I use a for loop to get those coefficients, then I can each time multiply that coefficient by the value in the nums array. So 1, 4, 6, 4, 1. So let's see. NCR is equal to n factorial divided by r factorial n minus r factorial. So n factorial is always the same. Generate binomial expansion coefficients in a for loop. What is the way to do that? Factorial. The factorial is going to be an issue because if I use factorial, then the number of rows in this, the number of rows here can be very large, like 1,000 factorial is just too big. Okay, Pascal's triangle. I think this is probably what I want. No, this also just iterates over too many. This makes it too many iterations. Yeah. This does basically the same process. This is, or has the same speed as what the current thing does. This just feels like it's just too... It's just too slow. Or not slow, but this thing is just factorial n is just too big. What is the largest factorial that Python can store many bits to store 1000 factorial. Seems like it'd be very large. Yeah, 8,000. 8,500 bits. That seems like it'd be too big. Hmm. 500 bits. Each Pascal's triangle is the sum of the two numbers directly above it. Nums has 1,000 length. I could do maybe find half the coefficients and then reverse mirror it to get the other half. Then you know the 146. Okay, so 4 choose 0 is 4 factorial divided by 0 factorial, 4 factorial, 4 choose 1, 4 factorial divided by 1 factorial, 3 factorial, 4 choose 2, 4 factorial, 2 factorial, 2 factorial. Okay, maybe there's just a Python binomial binom function. Is there binomial function? Binomial coefficient. Psi p. Okay, I guess maybe it's like a combination. How fast is this combination? Okay, let's try it. So n is the length of nums here. And we think actually I'll say n is the length of nums minus 1. And answer 0 for I wonder if I can do binom. Can I do mod 10 on this thing? Does this thing take a mod operator? Implementation of using a prime modulus. This is not prime modulus. Precompute the modulo p. Precompute the factorial modulo p. Oh, jeez. Okay. Yeah, I'm just kind of afraid how big the coefficients end up being. Oh well, we'll see how this goes. For every value in nums. I guess every index here. K in range of... Okay, this is stupid. K in range of n. Actually, maybe I should do this. Maybe I should do the coefficients in one go first. For K in range is n divided by 2. For 5 divided by 2 it should be 3. So for 2, I think it's n plus 1 divided by 2. I'll do coefficients and dot append GCF minus com math dot combinations and choose R. It's going to be n minus 1 is the number, k is the thing. Let's go ahead and just print that out. I think this should be right. Should be seeing 146, 146, 1, 146. Let's do one more test case. Let's say it's up to 6 values. No, that's still 146. I guess this should be 146. It should be 1, 5, 10. 1, 5, 10. Okay, that's right. And then I can do something like, I could probably even make that mod 10. Because yeah, I can make that mod 10. And then I think I can make it mod 10. Pretty sure. 12 times 3 is 36. 2 times 3 is 6. Okay. So for every k in range, the coefficients probably, length of coefficients. I can do that's not going to quite work. This is an odd number. Doing the coefficient is multiplying this first value, and the coefficient multiplies the last value from the end. I guess that's fine actually. Let's do it. Answer plus equals nums at k times coefficients at k plus nums at, I think it should be -1 minus k. That would work for the last one. If k is 0, then that works for the first one. That works for the last one. Coefficients at k as well. Now this works incorrectly for the middle one if it's an odd number. It works correct for the middle two, it's an even number. So I think I need to do an odd check. If n is odd, then I need to subtract the last extra bit. Actually, I think this should be mod 10. Well, it's not really going to get that large in this plot, to be honest. It's the coefficients that are large and the coefficients where I got mod 10, so they're going to be 1 through 10. This shouldn't get impossibly large at that point. So anyways, at this point, it's doing this one twice, so it needs to remove 1. Answer minus equals nums at the middle one. The middle one is index 2, which is going to be end of 2 times coefficients at the last. And the trick is if you're ever trying to figure out the correct indexing, you just think of an example and make the example work in your head. Unmatched parentheses. Okay, that was before I did the mod 10. Okay. Oh no. Okay. Well, that's faster, for sure. This peak is 13 milliseconds, so I mean, I know what I can do to actually do this. I could actually create the Pascal's triangle for 1 to 1,000, like hard code that into this answer. And then I don't need to recompute the coefficients. I'm not sure if that's what is being done here. It's being done here, but I have a suspicion that that is, because otherwise I don't see how this thing gets that much faster. Alright, let's try that. This is kind of the cheating way, or not really cheating, I guess, because pre-computing Pascal's triangle, if you know that this is your edge, your final case, then that might not be the worst thing. So let's go ahead and just pre-compute the binomial coefficients up to all for all possible values of n less than or equal to 1,000. I get Pascal's triangle. So Pascal's triangle what was the thing here? Start with 1, append the row, the sum of things directly above it. 1, 1, 2, So you do something like, well, yeah, you do that. So Pascal's triangle is going to be a 2D array. I guess it should start with 1. No. And then I guess the first row is going to be initially it's 1. Yeah. Maybe you can make initially just empty for every, let's say, R in K in range 1000. You add the sum of the first value is always 1. So new row is equal to 1. And then 1, 1, 1. You always start and end with 1. So you do something like for v in range of length of the current row minus length of the current row minus 1. New row appends rowic v plus rowic v plus 1. Those are your middle terms. And then you do new row append another 1. Row becomes new row. Pascal appends the row. At that point, we should have Pascal's triangle actually starting with a 1, I think. Yeah. First rows are in there. New row starts with a 1, doesn't add any middle things, adds an ending 1. So it's 1, 1. And then Pascal's triangle becomes 1, 1, 1. So Pascal's triangle. This might be too many lines. Oh, yeah, this needs to be mod 10, I think. Yeah. Otherwise, you can get way too much text here. Do. Huh. So it doesn't actually show it. Interesting. Um, one, two, three. Actually, maybe if I copy the standard out, does it actually have it? Yeah, it's just too much stuff here. Interesting. Interesting. There's a bunch of zeros. Guess when two zeros ever, at some point Pascal's triangle, all the coefficients probably end in 0. And if you ever have like zeros meet, then they're gonna become more zeros. It's kind of like a virus, maybe. Maybe. Wonder if at a certain level of Pascal's triangle, everything is zeros. Like 1, 7. You can't, right? You just can't. Because the second number in Pascal's triangle, any row is increasing number, so that increasing number should always have an ending value that's not always 0. Okay. It does seem to have it ends up with a lot of middle zeros. Okay. Um, Alright, I tried hacking my way to hacking my way to it, but didn't work out. I mean, I guess maybe you could store the first 100 lines of Pascal's triangle and say that that's going to be most of the test cases is probably going to be within that 100. So therefore, you don't have to do this slow operation for most test cases. That probably would be pretty reasonable, but I think I'm fine as is not trying to incorporate this. Okay. So summary here. This can be fairly straightforward to try the simpler approach, which is creating the rows individually as described in instructions. So can be done using for loops or using kind of list comprehension. to create the new rows each time. Faster way leverages the fact that the ending value can be calculated using binomial coefficients. Multiplying each value, multiplying corresponding values in a nums array. For example, given the example 1 array with 5 elements, 1, 2, 3, 4, 5, binomial coefficients for n equals 4, which is for the power equals 4, where the power is equal to n minus 1, is 14641, and the answer is equal to 1 times 1 plus 4 times 2 plus 6 times 3 plus 4 times 4 plus 1 times 5, which is something 48. Is it 48? Yeah, 48 mod 10, which is equal to 8. This is due to the fact that each value in nums contributes a different number of times, a number of times equal to their binomial coefficient to the end result sum. And you can shortcut that calculation of repeated additions using multiplying, using product of it and binomial coefficient. To quickly get the coefficients, use math.com with p the power and k the index. And that's this thing. With some slight optimization, you don't have to actually cut, since it's symmetric, the coefficients are symmetric, and you only compute the half of the coefficients. Like instead of computing 14641, you compute 46, and then use the 41 reversing the first half as surrounding. And then an extra optimization would be just using the half coefficients, or all the coefficients, and then multiplying that coefficient by the number at k and the number at like negative k, roughly. Negative 1 minus k. And then also just consider that the middle number might be duplicated at that point, then you need to remove the duplication if it's like a odd number of values in the nums. Small optimizations can be using like mirroring of coefficients. Only can be half. And particularly using mod 10 to shrink coefficients. Otherwise it's too big. If you calculate like the coefficients for the 1000th row of Pascal triangle. And then lastly, did not fully implement, but is possible, is pre-computing the coefficients for p less than or equal to 1000, so that to avoid the math combination calls completely, which is somewhat restricted due to Leetcode's max size on solutions. Like there's some limiting size that can submit. Time complexities can be, actually I'm not sure. Math that can be time complexity. It's not constant. Finally, determined by the number of arithmetic operations requires assigned to be efficient, especially when minimum of k and n minus k is small. For small values of n, where n is less than or equal to 62, larger value. Yeah, this depends on the time complexity of the math.com calls, which is certainly not constant for n, up to 1000. Although this is really implementation dependent. So dependent on the language, the math library that you might be using to here is for the simpler approach using for loops and this comprehension, that is of n squared, and the math.com approach is certainly faster than that. Space complexity, this is going to be O of if pre-computing the com values, then it is in fact O of n. You just do the multiplication of n values by those coefficients. Space complexity, this can be O of n to store some of the coefficients for reuse. I guess maybe you don't have to actually store it. You just create the coefficients and then use the coefficient to repeat that point. Actually, let me try this. answer plus equals. Yeah, I don't see why you wouldn't be able to use at that point. And at that point, you don't actually need to have the coefficient. Right, you just use the current coefficient. This current coefficient. And then you still need to have the odd cancellation. I guess this thing is just going to cancel using the last value of coefficient that was calculated. It's going to work when there's one value. Coefficient probably needs to be set to 1 here. That's the same speed. Alright, well, this looks is of 1. For the faster solution. For slower solution of n to store the n values in the latest row.